In this video, we're going to be looking at the greatest common divisor and the least common multiple. And we'll look at methods for finding the greatest common divisor and methods of finding the least common multiple. All right, let's look at this scenario for finding the greatest common divisor. You have two bands are to be combined to march in a parade. A 24-member band will march behind a 30-member band. The combined bands must have the same number of columns. Each column must be the same size. What is the greatest number of columns in which they can march? Okay. Here the bands could each march in 2 columns, and we will have the same number of columns, but this does not satisfy the condition of having the greatest number of columns. The number of columns must divide both 24 and 30. Now the numbers that divide both 24 and 30 are 1, 2, 3, and 6. So the greatest of these numbers is 6. So the first band would have 6 columns with 4 members in each column, and the second band would have 6 columns with 5 members in each column. So this is pretty much the definition of the greatest common divisor, or abbreviated as GCD. And it's sometimes, some textbooks call the greatest common divisor the greatest common factor, or GCF. Now this is for 2 whole numbers, A and B, not both 0. The greatest common divisor, or the greatest common factor, is the greatest whole number that divides both A and B. In other words, that's going to be the largest whole number that can go into the 2 numbers, A and B. One method of finding the greatest common divisor would be to use the colored rods method. In this case here, you're finding the GCD of 6 and 8 using the 6 rod and the 8 rod. And to do that, to find the longest rod such that we can use multiples of that rod to build the 6 rod and the 8 rod. In this case here, the 2 rods can be used to build both the 6 rods and the 8 rod. Okay? So here for the 6 rod, we can use 3 of the 2 rods, and for the 8 rod, we can use 4 of the 2 rods. So here we're using the 2 rod, which is the largest rod that can be built for 6 and 8 rods. 3 rods could be used to build the 6 rod, but not the 8 rod. The 4 rods can be used to build the 8 rod, but not the 6 rod. The 5 rods can be used to build neither, and the 6 rods cannot be used to build the 8 rod. So we can conclude that the greatest common divisor of 6 and 8 would be 2. Another method of finding the greatest common divisor would be the intersection of sets method. Here we can list all members of the set of whole number divisors of the 2 numbers, then find the set of all common divisors, and finally pick the greatest element in that set. Okay, this is the illustration of the intersection of sets method. To find the GCD of 20 and 32, denote the sets of divisors of 20 and 32 by D sub 20 and D sub 32, respectively. Here in this case, the divisors for 20 are going to be 1, 2, 4, 5, 10, and 20. And for 32, the divisors for 32 will be 1, 2, 4, 8, 16, and 32. Okay? Now, here we're going to find the intersection of those 2 sets, D sub 20 and D sub 32. When we find the intersection of 2 sets, we're finding the elements that are common in both of these sets. In this case, the 1, 2, and 4 are common in both d sub 20 and d sub 32. So here, the 1, 2, and 4 will be considered as common divisors. Okay. Now, in this case, the greatest number is 4. That will be your greatest common divisor. So here, for 20 and 32, the greatest common divisor of those two numbers would be 4. Next is the prime factorization method. To find the GCD of two or more non-zero whole numbers, we first find the prime factorizations of the given numbers and then identify each common factor of the given numbers. The GCD is the product of those common factors, each raised to the lowest power that the prime occurs in any of the prime factorizations. Numbers such as the number 4 and 9, whose GCD is 1, are considered to be relatively prime. Let's look at a couple of examples here. Using the prime factorization method, we want to find the GCD of 108 and 72. 108 is going to be broken up as 2 to the second times 3 to the second. And 72, if you use the factor tree, it'll be 2 to the third times 3 to the second. Okay, now we use each common factor. In this case, 2 is a common factor. It's in both 108 and 72. But for 2, we're going to use the lowest exponent of any of these two factorizations. The lowest exponent for 2 will be 2 to the second. So here we're going to use 2 to the second. And then 3 is common in both 108 and 72, so we use the 3. But we want to use the one with the lowest exponent, which is 2. So we use 3 to the second. So 2 to the second times 3 to the second, well, 2 squared is 4, 3 squared is 9, 4 times 9, that's 36. So the greatest common divisor of 108 and 72 would be 36. And then part B, finding the GCD of 0 and 13. Here, 13 divides 0 and 13 divides itself. So the GCD of 0 and 13 would be 13. Alright, part C, finding the GCD of x and y if x is 2 to the third times 7 to the second times 11 times 13, and y is equal to 2 times 7 to the third times 13 times 7. Okay, so here we're going to use the common factor with the smallest exponent. The 2 is common in both the x and the y, so we use that. The lowest exponent for 2 will be 2 to the 1, so we use just the 2. 7 is common in both of those, so we use 7. But we use the lowest exponent for 7, which is 2, so that's 7 to the second. We can't use 11 because 11 is not a factor in y. 13, we can use 13 because that's a common factor in both x and y. Now we can't use 17 because 17 is not a factor in x. So we got 2 times 7 to the second times 13. If you multiply this out, you get 1274. So the GCD of x and y would be 1274. Part D, finding the GCD of x, y, and z if x is 2 to the third times 7 to the second times 11 times 13. Y is equal to 2 times 7 to the third times 13 times 17. And z, which is equal to 2 to the second times 7. Notice that the 2 is common in all three, x, y, and z. But we use the 2 that has the lowest exponent. So we use 2 to the 1, or just 2. 7 is common in all three. But we're going to use the lowest exponent for 7, which is 1. 11 is not common in all three, and neither is 13 nor 17. They have to be common in all three of these terms. So in this case here, the GCD of x, y, and z will be 2 times 7, or 14. And part E, finding the GCD of x and y if x is equal to 5 to the 4th times 13 to the 10th, and y is equal to 3 to the 10th times 11 to the 20th power. As you can see, x and y have no common factors in them, so that means the GCD of x and y will have to be 1. And this is an instance where you have these two expressions that are considered to be relatively prime, because the GCD is 1. Another method is the calculator method. There are calculators that have the button that says SIMP. That key can be used to find the GCD of two numbers. So if we want to find the GCD of 120 and 180, we can press these keys, type in 120, then divide it by 180, and then hit the button that says SIMP, and then hit equal to obtain this display. Okay. And then we press the button that has the X, this type of key right here, and we see 2 on the display as the common divisor of 120 and 180. And then if we press that key again and keep pressing SIMP equals, and then press the X to Y key, we see 2 again as a factor. And then keep repeating the process to see that 3 and 5 are common factors. So here, the GCD for 120 and 180 is the product of the common factors 2 times 3 times 5, or 60. Okay, and I do have a calculator that has, and this is the TI-84 multi-view calculator. It does have this button that says SIMP. So if I wanted to do 120 divided by 180 and hit this button that says SIMP and then hit enter, I would get an error message. So it'd be better if I do this 120 and then hit this button that says N over D as a fraction, and then 180. And then hit your right arrow button, and then hit SIMP, then enter. Now you see 60 over 90, and then it says FAC, which means that 2 is a factor that was used. Because you divide 120 by 2, you'll get 60, and 180 by 2, you'll get 90. And there is a down arrow key that means, try it again, you'll see a factor of 2 is divided. That means that we divided the 60 and the 90 by 2 to get 30 over 45. And if I try it again, here this time the factor was 3. So we divided 30 and 45 by 3 to get 10 over 15. And then hit the button, SIMP button again. The factor is 5 that we use to get the 2/3. So as you can see, 2/3 is in simplest form. So that's where this comes from. 2 times 2 times 3 times 5. Okay, so the largest number that we use to reduce 120 over 180 would be 60. So that means your greatest common factor is 60. So pretty much this greatest common factor concept using a calculator is helpful in simplifying fractions, taking a fraction and writing it in its simplest form, because you're taking the greatest common divisor. Okay, the next method is the Euclidean algorithm method. If a and b are any whole numbers greater than 0 and a is greater than or equal to b, then the GCD of A and B is going to be equal to the GCD of R and B, where R is the remainder when A is divided by B. Finding the GCD of two numbers by repeatedly using the theorem above until the remainder of is zero is called the Euclidean algorithm. Okay, and this next thing I'm going to show you is the Euclidean algorithm method. First of all, you have to have positive numbers A and B where A is not equal to B. You're going to take the larger number and divide that by the smaller number. And then you're going to ask yourself, is the remainder 0? If it's not, then you're going to divide the last divisor by the remainder. And you'll continue this process until the remainder is 0. Once that remainder is 0, then the last divisor in the GC is that GCD of A and B. Okay, so this is just pretty much a flowchart of what the Euclidean algorithm method is. And let's look at how this is applied. We're going to use the Euclidean algorithm to find the GCD of 10,764 and 2,300. First thing we do is divide the larger number by the smaller number. 10,764 will be divided by 2,300. And then we divide 2,300 into 10,764. That's going to go 4 times. So 4 times 2,300 is 9,200. Subtract 9,200 from the 10,764, you're going to get 1,564. The remainder is not 0, so that 1,564 will be your divisor. This previous divisor, which was 2,300, will become the new quotient. So now you have 2,300 divided by 1,564. So how many times 1,564 will go into 2,300? 1 time. 1 times 1,564 will be 1,564. Subtract that from the 2,300, you're going to get 736, which is not a remainder of 0. So we're going to take that 736, that's going to become the divisor, and then the 1,564 becomes your dividend. So now you have 1,564 divided by 736. Ask yourself, how many times 736 will go into 1,564? That will go 2 times. 2 times of 736 will be 1,472. Then 1,472 divided by, 1,472 minus the 1,564 is 92. Still not 0, so we take that 92, which will be our divisor, divide that into the old divisor of 736. So 92 goes into 736 8 times. So 8 times 92 will be 736. Subtract that from the 736, you now have your remainder of 0. Okay, so here the last divisor, which was 92, that's going to be the greatest common divisor of 10,764 and 2,300, which is in this case 92. So this is how we use the Euclidean algorithm to find the GCD of a pair of numbers. Also, we can use the calculator to find the GCD using that Euclidean algorithm method. And this time you use the button that says INT division, okay, because it will give you the quotient and the remainder. So in this case here, if you take, and we're going to follow along here, and I'll clear this out, 10,764. Now, there's a button that says integer division, so I'm going to press second and then the division key for the integer division, which will give me the whole number and the remainder, and then 2,300, and then hit enter. Notice you get 4 with the remainder of 1,564. That's the quotient. The number after the R is your remainder. Okay, so we know the remainder is not 0, so here we take the old divisor, 2300, and then we're going to do an integer division of the remainder, which is 1564. Then hit enter. We get a 1, which is the quotient, but our remainder is 736. Okay, so our old divisor was 1564. We'll divide that by the remainder of 736. What I want to do is integer division. There we go. And then 736. And then hit enter. So now we got 2 with the remainder of 92. So now we take this 736 and then do integer division of 92. Hit enter. Here we got 8 with the remainder of 0. So that means that this last divisor that we used, which is the 92, that's going to be the greatest common divisor. Okay, so that's how you can use the calculator to do the Euclidean algorithm method. But it only works if you have the integer division key. And there are a few calculators that have that integer division key. Now let's look at one with 3 numbers. Find the GCD of 134,791, 6,341, and 6,339. Any common divisors of 3 numbers is also a common divisor of any 2 terms. So the GCD of 3 numbers can't be greater than the GCD of any 2 of the numbers. So if we take the 6,341 and 6,339 and get its GCD, that's going to be 1. Because notice 6341 and 6339, that difference is only 2. So it doesn't have any common divisors other than 1. And we know that it can't be greater than, the GCD of those 3 terms can't be greater than the GCD of any 2 terms. So if these 2 terms have the greatest common divisor of 1, then for all 3 of these terms, that greatest common divisor must be 1. Okay. Another example is find the GCD of any 2 consecutive whole numbers. Let's see, the GCD of n and then the next consecutive whole number will be n plus 1. Okay, so if you take n plus 1 minus 1 and then n, well, n plus 1 minus n will be 1, and then you have the GCD of 1 and n, which is 1. So the greatest common divisor of any 2 whole numbers will be 1. So for 13 and 14, the GCD is automatically going to be 1. Because 13 and 14 have no common factors other than 1. Okay, the next concept would be the least common multiple of 2 numbers. Let's say hot dogs are usually sold 10 to a pack, while hot dogs are usually sold 8 to a package. What is the least number of packages of each you must buy so that there is an equal number of hot dogs and buns? The number of hot dogs is a multiple of 10, while the number of buns is a multiple of 8. The number of hot dogs matches the number of buns whenever 10 and 8 have multiples in common. And this occurs at 40, 80, and 120. And it continues on and on. There's more of those common multiples. But the least of those multiples will be 40. So in this case, we'll have to have the same number of hot dogs and buns by buying 4 packages of hot dogs and 5 packages of buns. Okay, this scenario introduces the concept of the least common multiple, or the LCM, of 2 non-zero whole numbers A and B. And it's defined as the least non-zero whole number that is simultaneously a multiple of A and B. So when you're finding the least common multiple, you want to find the smallest multiple that's divisible by the 2 given numbers, A and B. One method of finding the least common multiple will be using the number line method. So here you want to find the LCM of 3 and 4. If you begin at 0, the arrows do not coincide until you reach to the point of 12, right here. Because those points do not coincide until you reach 12. So 12 will be the least common multiple of 3 and 4. Also, the colored rods method can be used to find the least common multiple, let's say, of 3 and 4. So here we got a 3 rod and a 4 rod. And we want to find the least common multiple. You want to build trains of 3 rods and 4 rods until they are the same length. The LCM is the common length of the train. Notice in this case here, you got the blue, each blue is a 4 rod, so you have 3 4 rods, and then the green is the 3 rods, so you have 1, 2, 3, 4 3 rods. The 3 4 rods will give you a length of 12. The 4 3 rods give you a length of 12. So the least common multiple of 3 and 4 would be 12. Also, the intersection of sets method. You want to list all the members of the set of positive multiples for the two integers. Then find the set of all common multiples, and finally pick the least element that's in that set. So in this case here, we want to find the least common multiple of 8 and 12. We want to denote sets of positive multiples of 8 and 12 by m sub 8 and m sub 12, respectively. So here for m sub 8, the multiples of 8 will be 8, 16, 24, 32, 40, 48, 56, 64, 72. And then for m sub 12, the least common those multiples of 12 will be 12, 24, 36, 48, 60, 72, 84, and 96. And then the intersection is the ones that are common in both m sub 8 and m sub 12. In this case, that's 24, 48, 72, and there are others. But we want the least number that's in that intersection. That's 24. So that 24 will be the least common multiple of 8 and 12. Then the prime factorization method is this. You want to find the LCM of two non-zero whole numbers. First, find the prime factorization of each number, and then take each of the primes that are factors of either of the given numbers. The LCM is the product of these primes, each raised to the greatest power of the prime that occurs in either of the prime factorizations. And to see how this statement works, finding the prime factorization, let's say we want to find the LCM of 2,520 and 10,530. For 2530, if you do the prime factorization using a factor tree, you'll see that it's going to break down to 2 to the third times 3 to the second times 5 times 7. And for 10,530, that number is going to break down to 2 times 3 to the fourth times 5 times 13. Now, to find the LCM, we're going to use each factor the greatest number of times that it occurs in any one factorization. We're going to use a 2, but we want the highest exponent for 2, which is 2 to the third. For 3, we want the highest exponent for 3, that's 3 to the fourth. The 5, we want the highest exponent for 5, which is 1, 5 to the first power. And then 7, it only occurs in one factorization, but we use that 7, and the same thing holds true with the 13. We use the 13 as well. Now, if you were to use your calculator to multiply all this out, you'll see that the least common multiple of 2,520 and 10,530 will be 294,840. And then we have the GCD LCM product method. For any two natural numbers, a and b, the GCD of a and b times the LCM of a and b will be equal to a times b. Like in this example, if we want to find the LCM of 731 and 952, we can apply the Euclidean algorithm to determine that the GCD of 731 and 952 will be 17. And then we take 17 times the least common multiple of 731 and 952, which will equal 731 times 952. And then in this case here, we just divide both sides by 17. You can get the least common multiple of 731 and 952, and that's going to be equal to 731 times 952 divided by 17 will give you the final answer of 40,936. Okay. So that's how you find the least common multiple of 731 and 952. Division by primes method is another way of finding the least common multiple of two numbers. To find the LCM of 1275 and 120, you're going to start with the least prime that divides at least one of the given numbers, and then divide as follows. In this case here, we can use 2. So here 2 will go into 2 will go into 12 6 times, 2 goes into 20 60 times. But because 2 does not divide 75, we just simply bring down the 75. To obtain the LCM using this procedure, we continue the process until the row of answers consists of relatively prime numbers as shown next. And here's that process. For 6, 75, and 60, we can use 2, because 2 goes into 6 3 times, 2 goes into 60 30 times. But 75 is not divisible by 2, so we bring down the 75. Now here they use the 2 again. 2 goes into 30 15 times, but 2 can't go into 3 nor 75 evenly, so the 3 and the 75 are brought down. So now for 3, 75, and 15, let's use 3. Because those numbers are not divisible by 2, so we need to try another prime number like 3. 3 goes into 3 1 time, 3 goes into 75 25 times, 3 goes into 15 5 times. Now let's deal with the 25 and the 5. Those are multiples of 5, so we can use 5 here. 5 cannot go into 1, so we bring that down. 5 goes into 25 5 times, 5 goes into 5 1 time. So here we got relatively prime factors here on the bottom row. Now to find the LCM, or the least common multiple, we're going to multiply all of these numbers on the left side and on the bottom. The left side is 2 times 2 times 2 times 3 times 5, and the bottom is going to be times 1 times 5 times 1. Simplify that, that's 2 to the third times 3 times 5 to the second, or you'll get 600. So the least common multiple of 12, 75, and 120 will be 600. Okay, so that will conclude this particular video on the greatest common divisor and the least common multiple.